So in this question, we're told that a research engineer is testing the effectiveness of the braking system of a car when it is driven in wet conditions. We're told that the engineer measures and records the braking distance, which is measured in meters and denoted by D, and that's the distance when the brakes are applied from a speed denoted by V, which is measured in kilometers per hour. We are given in figure 5 and figure 6, we're given the graphs of V against D and of log base 10 of D against log base 10 of V. And we can see here in figure 5, we have this curve and we see it passes through the point 30, 20 here. And then in figure 6 on the right hand side, we can see that if we take log base 10 of both sides, we have a straight line, which has y-intercept negative 1.77. And what we're asked to do in part A of this question is to explain how figure 6 would lead to the engineer to believe that the braking distance should be modelled by the formula d is equal to kv to the power of n, where both k and n are constants, and we're told that k is approximately 0.017. So given that d is equal to kv to the power of n, and we're told that k is approximately 0.017. So essentially what we're being asked to do is we're being asked to make a link between this formula here and figure 6. And we recall in figure 6 we had axis like this, where we had log base 10 of V plotted against log base 10 of D, and we had a straight line a bit like this. So that was a kind of general idea and a miniature sketch of what we had. So to go from this equation here into a form where we can link it to the figure, which was log base 10d against log base 10v, what we're going to do is we're going to take logs of both sides. So that means we'll have log base 10 of d is going to be equal to log base 10 of kv to the power of n. But what we can do, we know our log laws, and we can use log law number 1 here, in this case here, where a is equal to k and b is equal to v to the power of n. So that is going to equal to log 10 of k, and then we add the same log base 10, so log base 10 v to the power of n. And then we notice we can use our second log law here and take our exponent, in our case n, and place it in front of the log term. So continuing this on, we'll have log base 10 of k, and then we add on to that n log base 10 of v, and we know this is equal to log base 10 of d. So then the next thing, we recall that we're told in the question that k is approximately 0.017. So what we can do is we can substitute this in to this position here. So we'll then have that log base 10 of d is going to be equal to log base 10 of k. So we'll put in 0.017 plus n log base 10 of v, and then putting into our calculators we have the log base of 10 of 0.017, that is going to equal negative 1.7695 and so on. So then rounding that to 2 decimal places, we can say that log base 10 of d is equal to n log base 10 of v, and then we take away 1.77, where our negative 1.77 comes from here. So what do we have now? Well, we have something that has the components of our graph. So we recall that we had log base 10 of d against log 10 of v. So if we think of a normal graph where we have y against x, so if I just draw in purple on our little graph at the top, y against x, we can then see that we have something very similar. So if I then write y is equal to mx plus c, we can see that in this case, this is the equivalent to the equation of a straight line, where we have y is going to be equal to log 10 of d, where we have m is going to be equal to n, and then our x is equivalent to log base 10 of v in our case, and then we have the y-intercept, which is usually denoted by c, and it is negative 1.77. And from the sketch in figure 6, we know that the y-intercept is negative 1.77. So therefore, we have the linear nature of this coupled with the y-intercept, which tells us that figure 6 would lead the engineer to believe that the braking distance can be modelled by this formula here. And we've just manipulated it to show that. And writing this down, the linear nature and y-intercept in the equation matching that of figure 6 tells us that the braking distance can be modelled by d is equal to kv to the power of n. So in this part of the question, there was 3 marks on offer, and we received our first mark for successfully working out what the value of k was, and we receive our second mark at this stage here, where we write out the equation in terms of log base 10 of d and log base 10 of v. And then we receive our third and final mark for this concluding statement down here in the corner. So in part B of this question, we're told to use the information given in figure 5 with k equals 0.017, and we're asked to find a complete equation for the model giving the value of n to 3 significant figures. So we recall we'll have the following formula where the distance d is modelled by 0.017 multiplied by v, which is the speed, to the power of n, where n is a constant, and we're told to use the information given in figure 5. So taking a look at figure 5 just here in the corner, the main piece of information which we can read from this is the coordinates at a certain point. So we know that when x is equal to 30, y is going to be equal to 20. So therefore, we're going to substitute these into this equation. So writing this down, for the coordinates 30, 20, we'll therefore have that 20 is going to be equal to 0.017 multiplied by 30 to the power of n. So what we now need to do is solve for n. So making this slightly simpler, we can say that 30 to the power of n is going to be equal to 20, and we divide by 0.017, and this isolates 30n, and what we're now going to do is take log base 10 of both sides, which will mean we can then use the log law. Log a to the power of m is equal to m log a, where we take the exponent in front of the log term to then isolate n. So writing all this down, we'll then have that log base 10 of 30 to the power of n is going to be equal to log base 10 20, and we divide that by 0.017, and then we can use our log law, which I will write down here again just in case we've forgotten, where we have log a to the power of m is going to be equal to m log of a. So we can use this here to bring the exponent n in front of the log base 10 of 30. So then what we'll have is n multiplied by log base 10 of 30, and that's going to be equal to this term here, which remains the same. And then all that's left for us to do is to now divide both sides by log base 10 of 30, which can be written as follows, and we'll not simplify any of the log terms at the moment, as we're just going to put them into our calculator once we've written it out. 0.17, and we divide all of that by log base 10 of 30. And putting this into our calculator, it comes out as 2.07876. And recalling the question, we were asked to give a value of n to 3 significant figures. So therefore, we can say that n is going to be equal to 2.08. And then we look back at the question where we're asked to find a complete equation. So this then means we rewrite our equation but substitute n in. So therefore we'll have that d is equal to 0.017 multiplied by v to the power of our new value of n, which is 2.08. And there we have the complete equation for the model. So in this question, there was again 3 marks on offer, and we received our first mark for substituting in 30/20 into our expression for the distance. And we then received our second mark for carrying through the working and rearranging to solve for n, and saying that n is equal to 2.08. And then we received our third and final mark for rewriting our equation but with our new value of n substituted in. Then in part C of this question, we're given some further information. We're told that Sean is driving this car at 60 kilometers per hour, and we have wet conditions, and Sean notices there's a large puddle in the road, and it's 100 meters ahead, and it takes him 0.8 seconds to react before applying the brakes. And we were asked to use our formula to find out if Sean will be able to stop before reaching the puddle. So we recall our formula from the previous question, where we have d is equal to 0.017 multiplied by v to the power of 2.08. So we know that he will be able to stop before reaching the puddle if we work out that the distance travelled is less than 100 meters. So we know that the distance will have 2 components. So the distance will be made up of the before brakes plus the after brakes distances. So we know that once he notices a puddle, it takes him 0.8 seconds to react. So this means that in those 0.8 seconds, the car will still travel a certain distance, which has to be taken into account. This is the before brakes time. And then the after brakes time is where we use the model to calculate this distance. So firstly, we can calculate the before. So just noting this here, before brakes. So we'll have that the distance. So we'll note this as distance 1. And that is going to be worked out using speed multiplied by time. And we know that the speed of the car is 60 kilometers an hour. And then we want to multiply this by the time. But we know that the time is 0.8 seconds. But to convert this into the same units that the speed is measured in, which is kilometers per hour, we must change the seconds into hours. So we can do this by dividing 0.8 by 60 squared. So that's going to be 0.8 over 60 squared, which is 3,600, and that's going to be in hours. So therefore, we'll substitute this into our equation, and we'll have 60 multiplied by 0.8 divided by 3,600. And putting this into our calculator, this comes out as 0.0133. And we note that this is going to be in kilometers, but we're dealing with meters. So to get this into meters, we multiply by 1,000, which implies that the distance before the brakes are applied that the car covers is going to be 13.3 meters. So now we need to use our equation here to work out what the second distance is. So the distance after the brakes are applied, we'll denote that by d2, and it can be calculated using our model, where we sub in our speed v. So this is going to be 0.017, and we know now that v is 60, and we have that 60 goes to the power of 2.08, and putting this into our calculator, this comes out as 84.9 meters. So therefore, the total distance is going to be equal to 84.9 plus 13.3, which, putting this into a calculator, this is equal to 98.2 meters, which means we can conclude that Sean stops in time. So in this part of the question, there was again 3 marks on offer. We receive our first mark for working out the distance using our model, where we substitute 60 into our formula. So we receive this at this point here, where we worked out d2. So we then receive our second mark for working out the distance before the brakes were applied. So that came when we worked out 13.3 meters. So we then receive our third and final mark for concluding that Sean stops in time and that the total distance is 98.2 meters.